Hey, what's up YouTube? So here we are back again, day 13. Um, yeah, let me just scroll to our lesson here. So, alright, self-tuning model concepts. Combine regression and exponential moving averages to adapt coefficients over time. Okay, so it's getting a little harder. So this script yesterday, I just want to go over it again, just so it floats in, just so it sinks in. So this is our fake data. If you remember, these were delta temps. So this was zone temp and zone occupied zone set point deviation. N is the days, number of days of data that we have in here. These are some blank variables we're just defining. So yeah, this is some x, some y, some x times y, and then also x squared. So this is our delta temp squared. Kind of confusing. So yeah, let's go over it. So like what we're doing in this closed form mathematics is like we're summing over our little data structure here, and we're summing up our y's, summing up our each day in here. So we're like adding these together or multiplying or doing the x times x, the cube relationships, and like we're summing all those numbers together. Iterating through it, kind of brute force. Here's our closed form OLS coefficients. So this is like that denominator check. That's also in the Java code too. If there's not enough variation in delta delta temp squared in the Java code, that actually goes back to just default values for alpha A and alpha B. So this is how we're solving for alpha A, and this is how we're solving for alpha B on this equation. And also, like when we would iterate through our data and sum up all these, the units for alpha A, that was minutes per degrees Fahrenheit squared, which is the delta temperature, and then also the B parameter, alpha B, that was just minutes. So then those are actually added together to compute the effective minutes that we would be required to condition our zone. So it is, yeah, I think this stuff is getting kind of complex but kind of cool at the same time. So we just do our Python math lesson script. See what we got for print logs up to here. Okay, so this is this print log here, and then this is this one here. So with these two parameters, kind of looks like this. So actually, these are multiplied together, kind of like that y equals mx plus b style, fitting the line. So that's the model. Pretty cool. Okay, so now they're kind of getting like a little bit fancier, I think, in this AI generated lessons. I don't think we I am definitely not doing this in the Java code in the program object, but I think they're giving this now because like down the road, like week 5, like we get a little bit into like very primitive like machine learning models where we would be kind of computing some of this stuff. So I think that's why that they're giving that to us now. So this is SSE, which was the standard error for the fit, and then this is the standard error for the mean. So, and then we this is computing the error right here, and that was just to so we have something to compare it against. So that would mean, yeah, so basically I think if this was actually like real data, that this is the standard error of just averaged data, and then this is our model data, and since our model data is much better than our mean in terms of error, that we would say, hey, our model is good. A learned model beats the baseline mean, which is good. So these are, yeah, just if else. This is kind of cool. ChatGPT came up with this script. And then there's also, it also threw in some temperatures. So let's say tomorrow morning, so basically we train our model, and then we have to wait until the next day for the people to go home. They go sleep at night, and then the building drifts when the HVAC turns off. So when we're ready to start up next day, let's say our space temperature got down to 60 degrees. Here's our occupied space temperature, and then we use our model that we trained. And this is our little equation for model 1, defined by PNNL, and we would compute 64 minutes that our HVAC system needs to run to get that, to condition that zone for people to arrive the next day for a nice happy space temperature of 60 degrees, or 72 degrees space temperature set point. Okay, so that was kind of a doozy for me, but pretty cool to soak in. So let's jump right into day 13. Instead of recomputing alpha A and alpha B from scratch each day, you can apply an exponential moving average to these coefficients, blending yesterday's estimate with today's regression result. Interesting. This yields a slow drifting quadratic model that adapts to seasonal changes without overreacting to outliers. The update rule is analogous to the rate of exponential moving average from day 4. This seems kind of silly. I'm almost curious if the PNNL paper does this. I don't know if AI put this in here just for fun, because the PNNL paper doesn't even mention exponential moving averages to my knowledge last time I looked, so I'm kind of curious. Let's see, where were we? I think we were on this chat before, so let's see, so we were on day 13. Okay, so lessons, day 13, and I am going to even upload the PNNL paper, because I'm pretty sure that something seems kind of funny right here, why that they're doing the exponential moving average. So I'm just going to ask this. Whoops. In day 13, the EMA, this is confusing. Does the PNNL paper even mention EMA? Alright, let's see what ChatGPT comes back. Reading the documents, great question. Let's separate how the paper does. Yes, so the PNNL paper does mention EMA. Oh, okay. So section 2.2, thus an exponential moving average was applied to the daily update parameters, allowing the models to capture both recent and, okay, so I guess it does. That's interesting. Day 13 fields. Because these two learning layers are blended, layer 1, the P&L model 1 does not recompute coefficients using regression every day. Instead, it computes a daily slope estimates, for example. In EMA, smoothing over this is key. All right. So model 1 is actually doing daily parameter extraction. I thought it was actually computing the regression every day. So just to confirm this, so the paper states not to compute the regression every day. So then when would the requirements be, what would the requirements be to compute a new regression model? Okay, so let's see. Short answer. Looks like it's going kind of slow. Come on, ChatGPT. Network connection lost. Oh no. Maybe my internet is going kind of slow. Maybe while that kind of comes through, we can look at this a little bit in more detail. So we will have to do this lesson then. So here's a simple Python demonstration, self-tuning. So so if I understand this right, this is our alpha B, alpha A parameters. And that they're just, instead of updating the raw values every day with a regression, that they're kind of using exponential moving average then. So let's copy this in our Python code. Maybe I'll put it down on the bottom. So now we would just have to actually factor in how to use this with the rest of our script. So initial estimates. So actually, like, we could just kind of go off of our previous script. Self-tuning quadratic coefficients. Let me just see if we have this. So maybe we could I'm just gonna do this. So alpha A existing, alpha B, B existing. Curious if this would solve our lesson requirement for today. So simulate a five days. Try refreshing you. Ooh, all right, so it looks like we try again. Must have had an internet glitch there. All right, so the P&L does not intend for you to compute a full regression every day. They intend daily physics-based requirements in EMA smoothing. A full regression is optional and only needed in specific situations. Interesting, I did not know this. So P&L Model 1 assumes each day you observe, delta t, the minutes, and then from a single day observations, you compute the raw coefficients, which we've been doing. That raw estimate is noisy, so you EMA it with past values. That is not regression, it's online adaptive estimation. Cool. Yeah, this is interesting. Okay, so I'm just kind of curious, how is this for day 13 lesson to use day 12 script? And then our day, say I'm trying to do this. I'm trying to do this. Is it really good? Okay, to reuse, so blah, 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 blah. Don't reuse the names. All right. So that's fitting our model. Looks like they're doing just a little function, which is kind of cool. Should be pretty easy to follow. And then they return alpha A, alpha B, standard error for the fit, standard error for the mean. Wow. Okay, so we have to save our past performance data, and we have to save our past regressions. Jeez. So it's getting complicated. Pretend these are regressions, so these should be alpha A, alpha B parameters that we have saved, and then we run an exponential moving average across the EM, across our coefficients, compute new coefficients every time that it runs. Wow. Micro exercise B, why tune alpha differently for A and B? Demo this on 2 different alphas. Respond moderately to the changes in slope. Optional. Different EMA rates for A versus B. So they're just saying, we'll just get different numbers. We'll start pumping out different, your minutes calculation will be all over the place. Well, this is interesting. I'm just going to delete this and just kind of say, responds moderately to changes in slope, responds slowly to intercept drift, often noise delay. Cool. I think I'm going to keep this, and this is kind of cool that we have another updated script. Wow. Well, just to recap, this would be our delta t, our minutes that we would from our run history, and then these are our daily coefficients. Interesting. Okay, so I think I might stop it for here, guys, and then I almost want to say that we might be getting to the end of, let's see, so day 14, which should be the end of model 1 versus 0. Okay, so starting to get complicated, at least for me. Definitely learning a lot here. There's actually a lot that goes into this optimal start mathematics, and it's getting interesting. So thank you for following along if you've made it this far. See you tomorrow.